Hello, everyone. Welcome to the third lecture of AAE 301. In today's lecture, we will talk about inner product spaces and review some concepts from linear algebra. So first, let's take a look at what a linear space is. And let's do this by going through the definition together. We say that H is a linear space if F and G are vectors in H, then any linear combinations of F and G is also a vector in H, where alpha and beta are complex numbers. So essentially, this means that if the set H is a linear space, then if you take any two vectors from the set H, and then any linear combinations of these two vectors will also be in this set H. So now let's take a look at an example. First, we let C be the set of all complex numbers. And here we let C new to be the set of all new tuple of the form F equals to F1, F2, all the way to F new. And here F1, F2, all the way to F new are complex numbers. And here new is just a positive integer. And now we are going to show that C new is a linear space. And to help you understand better, let's just assume that new is equal to 3. So here we are going to show, I'm going to show you that C3 is a linear space. So to do that, let's first pick a vector from C3, and let's call it F. And F is going to be this vector here, F1, F2, F3. And now we pick another vector in C3, which we call it G, and G is equal to G1, G2, G3. And now to show that C3 is a linear space, we will have to look at the linear combination of F and G. So here we look at this alpha F plus beta G, and alpha and beta here are complex numbers as well. And now we know because F is equal to F1, F2, F3, and G is equal to G1, G2, G3, we know that alpha F plus beta G will equal to alpha times F1, F2, F3 plus beta G1, G2, G3. And this will give us alpha F1 plus beta G1, alpha F2 plus beta G2, and alpha F3 plus beta G3. And now if every component inside this vector is a complex number, then this implies that C3 is going to be a linear space. So now let's check if every component inside this vector is a complex number. So here we have the first component, alpha times F1 plus beta times G1. So here, alpha and F1 are both complex numbers, and we know that the product of two complex numbers will also be a complex number. So this is going to be a complex number as well. And now let's look at beta time. Now let's look at beta G1. And similarly, both beta and G1 are complex numbers. So the product of these two complex numbers will also be a complex number. So now we have two complex numbers summing together, and we know that the sum of two complex numbers will also be a complex number. So this means that alpha F1 plus beta G1 is a complex number. And the same result can be applied to the other two components, alpha F2 plus beta G2 and alpha F3 plus beta G3. So this means that uh, alpha F plus beta G is going to be in C3 as well. And this means that, this means that C3 is a linear space. And you can further show that this holds for all positive integer nu. So this implies that C nu is a linear space. Okay, now let's take a look at how we can measure the distance between two vectors in a linear space. And to do that, we will need to introduce the concept of inner products. So here, the inner product is, this is the inner product, or sometimes we call it the dot product. And this is, and essentially this is a complex value function that maps that maps any elements in h times h into the complex number set C. So essentially this means that this function will take two vectors in h as an input, and it will produce an output that is in the complex set. So in order for this function to be inner product, it will have to satisfy the following four properties. The first property is the conjugate symmetry. So the conjugate symmetry is when you look at the inner product of f and h, the result will be the same as the complex conjugate of the inner product of h and f. All right. The second property is the linearity in the first element. So that's when you look at the inner product of alpha f plus beta g and h, then the result will equal to alpha times the inner product of f and h plus beta times the inner product of g and h. Now the third and the fourth property are called the positive semi-definiteness. So positive semi-definiteness. So that basically this implies that when you look at the inner product of a vector and itself, it will always be no less than 0. And it will only be 0 when the vector that we are looking at is 0. All right. So yeah. So now for a function to be an inner product function, it will have to satisfy all these four properties. And now let's take a look at another extension that we can obtain from these four properties, which is the inner product is conjugate linear in the second variable. So here, if we look at the inner product of h and alpha f plus beta g, then according to the first property, we know that this will equal to the complex conjugate of the inner product of alpha F plus beta G and H. And then by the second property, we know that this inner product will equal to alpha times the inner product of F and H plus beta times the inner product of G and H. Okay. And then now it will be this can be rewritten as the complex conjugate of alpha times the complex conjugate of the inner product of F and H plus the complex conjugate of beta times the complex conjugate of the inner product of G and H. And then according to the first property, we can rewrite the complex conjugate of the inner product of F and H as the inner product of H and F. And similarly, the complex conjugate of the inner product of G and H can be rewritten as the inner product of H and G. So that's the end. That's what we get in the end. So now that we have talked about the inner product, we are going to talk about what an inner product space is. So inner product space is essentially two things. So first, we will need to have a linear space. And we defined an inner product for this linear space. Oops. Then the result we get will be an inner product space. And for when we have an inner product space, then we can measure the distance between any two vectors in the linear space or in the inner product space. So for example, we can define the norm of a vector. Essentially, the norm will be the distance of that vector from the origin. So here we will define the norm of a vector f in the inner product space as the square root of the inner product of f and itself. And we can also define the distance between two vectors in the inner product space. So the distance between two vectors f and g will equal to the square root of the inner product of f minus g and f minus g. Okay. And when the linear space H is C nu, then we can define something called when the linear space H is C nu, there are actually many ways to define an inner product. And the standard way is this one. So the inner product of F and G is equal to the complex conjugate transpose of G multiplied by F. And this will give us, so if G is, so if F, so if F is equal to F1, F2, all the way to G, all the way to F nu, and G is equal to G1, G2, all the way to G nu, then the complex conjugate transpose of G will be G1, the complex conjugate of G1, the complex conjugate of G2, all the way to the complex conjugate of G nu times F1, F2, all the way to F new. And the result will be G, the complex conjugate of G1 times F1 plus the complex conjugate of G2 times F2 plus all the way to the complex conjugate of G new times F new. And we can write this summation in a more compact form as GK, the complex conjugate of GK times FK, and K is from 1 to new. And we can also flip this. So we can rewrite this as Fk times the complex conjugate of Gk, and K is from 1 to new. And this is the standard inner product. This is the standard inner product for C new. So now that we have defined the standard inner product for C new, we can see, we can now have another expression for the norm of a vector in C new. So recall that the norm of a vector f is defined as square root of the inner product of f and itself. And now we know what the inner product of f and itself is. It is essentially going to be the sum of k equals to 1 to new and fk times the complex conjugate of fk. And we know that when you have a complex number multiplied with its complex conjugate, what you will get is the squared of the absolute value of that complex number. So here, the norm of f will become the square root of this summation here, fk squared. All right, this is norm of f. Oh, sorry, norm of f. And now let's look at how we can measure the distance between two vectors in C nu with the standard inner product. So here we look at the distance between f and g, and by the definition, it is equal to the square root of the inner product of f minus g and f minus g. So the inner product of f minus g and f minus g is the summation of fk minus gk times the complex conjugate of fk minus gk, and k is from 1 to new. And this is equal to the square of the absolute value of fk minus gk, and k is from 1 to new. So eventually we will get the distance between f and g equals to the square root of this dimension here, fk minus gk squared. All right, and now it's time for some examples. Say, let's look at these two vectors in C3. So f is equal to 2i 3 plus I, and g is equal to 2 minus I, 1 plus I, and 2. Okay. And the first thing we check is the inner product of f and g. So the inner product of f and g will be the complex conjugate transpose of g multiplied by f. So that's gonna be 2 plus I, 1 minus I, 2 times 2I, 3 plus I. And the result will be 2 plus I, plus I, 1 minus I, plus 3 plus I times 2. So now let's expand this. We get 4 plus 2I plus I plus 1 plus 6 plus 2I. And now we sum up the real parts. We get 11, and sum up the imaginary parts. We get uh, 2 plus 1 plus 2, that's 5. So that's 11 plus 5. And now let's look at, say, the the squared norm of f. So the squared norm of f will be uh, essentially just the inner product of f and itself. So this is going to be the f. Uh, this is just going to be the summation of fk squared. K is from 1 to 3. So here that's gonna be 2 squared plus 1 squared plus 3 squared plus 1 squared. And that's 4 plus 1 plus 9 plus 1. So 50. Similarly, the squared norm of G will be the inner product of G and itself. And that's gonna be a summation of the square of the absolute value of gk, and k is from 1 to 3. And in this case, that is going to be 2 squared plus negative 1 squared plus 1 squared plus 1 squared plus 2 squared. And now we expand this, we get 4 plus 1 plus 1 plus 1 plus 4. So that's 11. And we can also compute the squared distance, the square distance of between f and g, and that's essentially just going to be the inner product of f minus g and f minus g. And first, let's compute what f minus g is. So f minus g is going to be 2i 3 plus I minus 2 minus I 1 plus I 2, and that's equal to I and negative 1 and 1 plus I. So the inner product of f minus g and f minus g will be this summation here, fk minus gk squared, and k is from 1 to nu. So that's gonna be 1 squared plus negative 1 squared plus 1 squared plus 1 squared, and that's 1 plus 1 plus 1 plus 1, which is 4. Okay, great. All right, now let's take a look at another linear space. This is the Basque space. It's denoted as L squared and 0 to tau. And here tau is just a positive real number. And this is the Basque space. Let me write this down. This is the Basque space. So the Lebesgue space is the linear space consisting of the set of all functions ft that is defined on the interval 0 to tau that satisfy this inequality here. 0 to tau ft squared dt is smaller than infinity. And here ft is um, defined on 0 to tau, and it's a function. It will return a complex value. And uh, to help you understand this space better, let's look at one example. Say this L squared 0 to 2 space. So in this case, tau equals to 2. And in this space, and t squared, sorry, the function t, the function ft will be an element inside this space. Oops. The function ft equals to t will be a function inside this space. And now let's show that. So for this function to be inside this space, it will have to satisfy the integral inequality that we have just seen. So now let's see that if if this function satisfied that inequality. So we look at the integral from 0 to 2, and then here we have the square of the absolute value of f of t and times t. And in this case, f of t is t, so we substitute that in. I should here. So here we have 0 to 2, and then t. And here what I did is I substitute tau equals to 2 and ft equals to t. And because t is a real number, so and also t is positive from 0 to 2, so we can remove the absolute sign, and what we'll end up with is just t squared, t. So this is something that can be solved easily. So this will be t cubed over 3 from 0 to 2, and that's gonna be 3 and 8 minus 0, so that's 8 over 3. So obviously 8 over 3 is finite, so that means it's smaller than infinity. So this means that t, the function ft equals to t is inside the Lebesgue space L squared 0, 2. Okay, so for this Lebesgue space, we can define another standard inner product. So that will be fg, the inner product of f and g, will equal to 1 over tau 0 integration from 0 to tau times ft times the inner the complex conjugate of gt. And now that we have defined the inner product, we can then define, we can now write out the expression for the norm of f, the norm of a vector or a function f inside the Lebesgue space. So again, we start from the definition. The norm of a vector will be the square root of the inner product of f and itself. And in this case, we know that the inner product is the inner product of f and itself is 1 over tau integration from 0 to tau f of t multiplies by the complex conjugate of f of t times dt. And because f of t and f of t is will return a complex number, and this will also be a complex number. Oops. Because f of t is a complex number, And so when you have a complex number multiplied by its complex conjugate, what you will get is the squared of the absolute value of the complex number. So here we will have 1 over tau, 0 to tau, and then f of t squared t. So this means that the norm of f will just be the square root of 1 over tau times 0 to tau f f of t squared dt. Okay. And we can also measure the distance between two vectors in the Lebesgue space. So we can measure the distance between f and g, and that's gonna be the square root of f minus g, the square root of the inner product of f minus g and f minus g. And here we have the inner product of f minus g and f minus g equal to 1 over tau, integration from 0 to tau, f ft minus gt multiplied by the complex conjugate of ft minus gt dt. So again, here we would, so again, this is ft minus gt will be a complex number. So when you have a complex number multiplied by its complex conjugate, you'll get the square of the absolute value of that complex number. So you get this thing here. And so now we substitute this back into the expression above, and we will get the distance between f and g equal to the square root of this whole thing. Okay. And now let's take a look at some examples. So here we're gonna look at the Lebesgue space 0 to 2. And you can show that these functions are all in the Lebesgue space. So t squared, and also 1 minus it, and t quadrant, and also 1, the constant 1. And so they all belong to the Lebesgue space, L squared 0, 2. And now let's look at the inner products of these vectors or functions in the space. So first, let's take a look at the inner product of t and t squared. So that will be, let's follow the definition first. So we will have, so the inner product, let me write this down first. So the inner product of f and g will be 1 over tau, and then 0 to tau, f t times the complex conjugate of gt times dt. So here we have t and t squared, and so here we have f equals to t, and g equals to t squared, and tau equals to 2. So here we look at the inner product of t and t squared. We will have 1 over 2, and integration from 0 to 2, and t times the complex conjugate of t squared times dt. So that's gonna give us 1 over 2, 0 to 2, t, and because t squared is a real number, so the complex conjugate of the real number is the real number itself. So here we're left with t squared times dt. So, oops. So here we have 1 over 2, 0 to 2, t cubed dt. And that's gonna be 1 over 2 times quadrant of t over 4 and 0 to 2. So eventually we will get 16 over 4 minus 0, and that's gonna be 2. Great. And let's take a look at another example here. We look at the inner product of t and 1 minus it. So here it's going to be 1/2 and integration from 0 to 2 t times the complex conjugate of 1 minus it dt. And that's going to be 1/2, 0 to 2 t times 1 plus it t. And that's going to be 1/2, 0 to 2 t plus it squared dt. And now we can work out this integral. We get t squared over 2 plus I times t cubed over 3 evaluated at 0 and 2. So that's going to give us 1/2 times 4/2 plus I times 8/3. So in the end, we get 1 plus I times 4/3. Okay. And let's take a look at yet another example. Let's look at the distance between, the norm of 2 minus 3 ti. So to compute this, let's first compute the squared norm of 2 minus 3 ti. And that's basically gonna be the inner product of 2 minus 3 ti and itself. So we would have 1/2, 0 to 2, 2 minus 3 ti times the complex conjugate of 2 minus 3 ti dt. And because this is a complex number, so we have a complex number multiplied by its complex conjugate. What we'll get will be the squared of the absolute value of 2 minus 3 ti dt. And this will be for, oops, I should write it like this. It should be 2 squared plus -3t squared dt. So here we would have 1/2, 0 to 2, 4 plus 9t squared t. And then this is going to be 4t plus 3t cubed. Oh, sorry. This would be 4t plus 3t cubed from 0 to 2. So that's 8 plus 3 times 8. And that's 32 divided by 2, 16. So this implies that the norm of 2 minus 3 ti will be the square root of 16, which is, all right. Now let's talk about another important concept in linear algebra. It is the orthogonal basis. So first, let's consider this inner product space H. So H is a linear product space. Oh, sorry, it's an inner product space. And we let F and G be two vectors in this space. And we say these two vectors are orthogonal if the inner product of f and g equals to 0. So here, this means orthogonal. Okay. And now if we have a set of vectors from H, let's call this set M. And we say F is orthogonal to this set of vectors if F if the inner product of F and any vector in any vector G in M equals to 0. So here G is any vector in M. Okay. Now let's look at the set of vectors which we called psi k, and k is in this set kappa. And here kappa is a set of integers. So for example, you can think about kappa as 1, 2, 3. So in this case, psi k, k equals to kappa will be psi 1, psi 2, psi 3. Okay. So we say that this set of vectors is orthogonal if the inner product of any two vectors, any two different vectors is 0, and the inner product of the vector and itself, the inner product of a vector and itself will be just the squared norm of that vector. So this is for any k and m, for any two different for any two different integers, and this is for all k for all k in this composite. And here k and m are both in this composite as well. And furthermore, we say that this set psi k, k in kappa, is a set of non-zero orthogonal vectors if all the vectors in this set are non-zero. So is not non-zero orthogonal if psi k is not 0 for all k in the composite. Okay. Now here's another thing from linear algebra. So if we have this set of non-zero orthogonal vectors, they are non-zero. Oops. Zero orthogonal, then this implies that this set is this set of vectors is linearly independent. So just as a review, let's take a look at the set we have just seen, psi 1, psi 2, psi 3. So if this set is linearly independent, it basically means that psi 1 cannot be uh, uh, obtained by a linear combination of psi 2 and psi 3. And psi 2 cannot be formed as a linear combination of psi 1 and psi 2. Sorry, psi 3. And psi 3 cannot be formed as a linear combination of psi 1 and psi 2. This implies this set is the, uh, the linearly independent. So if you think of this, so this implication actually makes a lot of sense, because if you have a set of non-zero orthogonal vectors, they are basically going to be perpendicular to each other. So obviously, when you are looking at, say, uh, this direction cannot be obtained by any linear combinations of the vectors in these two directions, because any linear combinations of these two vectors uh, will actually just form a plane, which is this plane. And you can see that this plane is perpendicular to this orange direction. So there's no way to obtain this direction with a linear combination of these two vectors. And you can verify the same. You can verify for the other two vectors as well. And in the end, you will see that for a set of non-zero orthogonal vectors, it's going to be linearly independent. And if you wanted to show this mathematically, you can refer to the proof here. And now let's talk a little bit more about the orthogonal basis. So let's go through these lines together. The first point is the dimension of a linear space H is the number of linearly independent vectors needed to span H. The second point is dimension of C nu is nu. So essentially that means that you need at least you need new linearly independent vectors to span the linear space C nu. And if the set of vectors is a linearly independent set of vectors in C nu, then this set of vector is a basis for C nu. So basically that means that for any vector in C nu, it can be uh, it can be obtained as linear combinations. Sorry, linear. Yes, linear combinations of vectors in this set. And the next point says, if the set of vectors is any non-zero orthogonal set of vectors, then this set of vectors is going to be a basis for C nu. And this is pretty straightforward, because we know that if this set of vectors is a non-zero orthogonal set of vectors, then they are going to be linearly independent. And the last point says, if the set is an orthogonal basis for H, the last point says the set of vectors is an orthogonal basis for H if this set of vectors is a non-zero orthogonal set of vectors, and given any vector f in H, then there exists a set of scalars such that f can be obtained as the linear combinations of these vectors. So for example, here we have a non-zero orthogonal set of vectors in C4. So they are this set. So this is 1, 0, 0, 1, 0, 1, 1, 0, and 2, 0, 0, negative 2. And 0, 3, negative 3, 0. So first thing we check, so we claim that this is a non-zero orthogonal set of vectors. So this is non-zero. So first thing we check is whether these vectors are non-zero. So obviously we see that they are now zero, right? So none of them are zero. And now we check if this is indeed, if these vectors are indeed orthogonal to each other. So let's call this v1, v2, v3, and v4. So now we look at the inner product of v1 and v2. We see that it's going to be uh, the complex conjugate of v2 times v1, and that's going to be 0, 1, 1, 0 times 1, 0, 0, 1. And if you multiply it out, you get 0. So v1 is orthogonal to v2. And now let's see v1, whether v1 is orthogonal to v3. So that's going to be v3, the complex conjugate transpose of v3 times v1, and that will be 2, 0, 0, negative 2 times 1, 0, 0, 1. And that is going to be 2 minus 2, which is 0. So this means that v1 is orthogonal to v3. And say v1, let's look at the inner product of v1 and v4. And that's v4, the complex conjugate transpose of v4 times v1. And that will be 0, 3, negative 3, 0 times 1, 0, 0, 1, and we get 0. So v1 is orthogonal to v4. And you can check the rest by yourself. So they are v2, v3, and v2, v4, and also v3, v4. So I believe in the end you will see that uh, any two vectors, any two different vectors in this set will be orthogonal to each other. So they are all going to be 0, and this implies that this set of vectors is a set of non-zero orthogonal set of vectors. All right, and this set of non-zero orthogonal vectors is actually going to be a basis for C4, for the linear space C4. And also, you can see that the dimension of C4 is obviously 4, right? Because here the dimension will equal to the cardinality of this set, of the set of vectors. And here we have 4 vectors in this set. So the cardinality of this set is 4. And that's going to be exactly the dimension of C4. Essentially, that means that any vector in C4 can be obtained by a linear combination of these 4 vectors. Right, now let's continue with the theorem shown here. So let's go through this. Let's go through this theorem together. Um, Here we let this set of vectors to be an orthogonal basis for an inner product space H. Then any vector f in H will emit a unique representation of the form f equals to the summation of ak times psi k, where psi k is the vectors in the set, and um, here ak are going to be scalars. So that means, let me write this down. So here we have f equals to summation k, k belongs to the set kappa, and ak times psi k. And here psi k is from this set of non-zero orthogonal vectors. So here this is k, kappa. K belongs to kappa, and here ak will be scalars. This is orthogonal basis. So essentially what this says is AK will be the coordinates of this vector in this orthogonal basis. So and to obtain the coordinates, what we do basically is inner product. So here we have f, the inner product of f and psi k. So to find the let's say now we want to find the coordinates ak. This coordinates ak can be obtained by dividing the inner product of f and psi k by the norm squared of psi k. And now let's see why this works. So first, we replace f with the summation. So here we have summation of ak times psi k, and k is from k for all k in the kappa set, and the inner product of psi k. And here we divide it by psi k, the norm square of psi k, sorry. And um, we know that because this set of vectors is an orthogonal set of vectors, so any inner product, the inner product of any two different vectors in this set will be 0, and the inner product of psi k and itself will just be the norm squared of psi k. So you see that uh, we have this summation here can be rewritten as ak times psi k plus the summation of all the other k's. Sorry, maybe let me write it in a different way. Here we have m, and this is am and psi m, and this is psi k divided by psi k squared. So here we will have ak psi k, the inner product of ak and psi k plus the summation of all the other elements in the set kappa, am times psi m and psi k divided by the norms, the squared norm of psi k, and this term here will be 0 because this is a set of orthogonal vectors. So in the end, we will be left with the inner product of ak psi k and psi k divided by the square norm of psi k. So this is going to be basically just ak times the square norm of psi k divided by psi k, the square norm of psi k, and so in the end we have ak. Great. And another thing is we will have this thing called Parseval's equality that says the squared norm of f will be equal to this summation here. So the square of the absolute value of ak times the square of the norm of psi k squared, and k for all k in the set kappa. So how can we obtain this equality? Now I'm going to show you this. So recall that the squared norm of f is essentially going to be the inner product of f and itself. So here let's replace f with the summation ak times psi k, and the summation ak times psi k, and k is in kappa set. And now you will see that so let's assume that uh, kappa equals to 1, 2, and 3 for the simplicity of the explanation. So we would have summation of a1 psi 1, a2 plus a2 psi 2 plus a3 psi 3, inner product with summation of A1 psi 1 plus A2 psi 2 plus A3 psi 3. And you see that in the end, we will be left, if we expand this, what we will be left with is going to be the inner product of A1 psi 1 and A1 psi 1 plus the inner product of A2 psi 2 and A2 psi 2 plus the inner product of A3 psi 3 and A3 psi 3. Because if you look at uh, the inner product of, so so if you look at the inner product of A1 psi 1 and say A2 psi 2, you see that this will be 0 because psi 1 is orthogonal to psi 2. So what we will be left with is just the inner product of A1 psi 1 and itself, and the inner product of A2 psi 2 and itself, and A3, the inner product of A3 psi 3 and itself. So for this inner product, what we'll get is, for these inner products, what we'll get is uh, uh, so let's write this way. So we have A1 psi, the complex conjugate transpose of A1 psi 1 and times A1 psi 1 plus the complex conjugate transpose of A2 psi 2 times A2 psi 2 plus the complex conjugate transpose of A3 psi 3 times A3 psi. And this will become A1's the square of the absolute value of A1 times the norm, the squared norm of psi 1 plus the square of the absolute value of A2 times the square of the norm of psi 2 plus the square of the absolute value of A3 times the square of the norm of psi 3. So we can write this in a more general way as f, the square norm of f will equal to the summation of ak, the squared of the absolute value of ak times the squared of the norm of psi k. Here k is in this concept. All right, so this is how we can obtain the Parsifal's equality. And here we have another corollary. So let's go through this corollary together. So here we let this set of vector be an orthogonal basis for an inner product space H. And we let K1, kappa 1 and kappa 2 be two distinct subsets of K, satisfying the union of kappa 1 and kappa 2 equals to K. So essentially, this means that if kappa is 1, 2, 3, 4, then we can let kappa 1 equals to 1 and 2, and kappa 2 equals to 3 and 4. So you can see that kappa 1 and kappa 2 are two distinct subsets of K. Sorry, of kappa, and the union of kappa 1 and kappa 2 will be K. Right? And finally, we let f equals to the summation of ak times psi k, and k is in this kappa set, be a series representation for the vector f in H. Then the distance between f and the vector p, which is formed by the summation of ak times psi k, and k is in the kappa 1 set. And the distance will be given by f minus this p, right? And this can be rewritten as f minus summation k kappa 1 ak psi k. And what we will be left with is just going to be uh, that we can rewrite this as we can rewrite f as summation k in kappa and ak psi k minus summation ak psi k and k in kappa 1. And what we'll be left with will be the case in the set kappa 2. So here we can rewrite this as k in kappa 2 ak psi k, and to obtain the norm of this remaining vector here, uh, we can apply the Parsifal's equality again, and you will see that this will end up being the summation of ak squared, the squared of the absolute value of ak times the squared of the norm of psi k, and k is in the kappa 2 set. And because this is the norm, not the square root of the norm, so we have to take the square root of it. And this will be the distance between f and the approximation p. All right, now let's talk about the other concept, which is related to the orthogonal basis. Uh, this is the orthonormal vectors. So just now we have seen that if a set of if this is a set of vectors, uh, and this set of vectors is orthogonal, if any two different vectors in this set is orthogonal to each other, and then we will say this is a orthogonal set of vectors, right? If psi k times psi m is 0 for k not equal to m, and k m are in this set, and psi k is equal to psi k squared for all k in the kappa set. And furthermore, we say if psi k is non-zero for all k in the kappa set, then this set will be a non-zero orthogonal set of vectors. And furthermore, if the norm of psi k is equal to 1 for all k in this kappa set, then we will say this set of vectors is a orthonormal set of vectors. So here I'm going to show you an example of an orthonormal basis for C3. So the first, so let's consider this set of vectors, um, phi1, phi2, phi3. Oops, phi1, phi2, phi3, and they are square root of 2, 1, 1, 0, and 1 over square root of 2, 1, negative 1, 0, and 0, 0, 1. So obviously, we see that this is a non-zero set of vectors because none of these vectors is 0. And the other thing we check is if these vectors are perpendicular to each other. So let's look at the inner product of psi 1 and psi 2, and the inner product of psi 1 and psi 3, and the inner product of psi 2 and psi 3. So the inner product of psi 1 and psi 2 will be psi, the complex conjugate transpose of psi 2 times psi 1. So that's 1 over square root of 2, 1, negative 1, 0, and times 1 over square root of 2, 1, 1, 0, and that will be 1/2 times 1 minus 1. That's 0. So that's 0. So this implies that psi1 is perpendicular to psi2. And here we have psi2 and psi3. So sorry, I should be psi1 and psi3. So that's a complex conjugate transpose of psi3 times psi1, and that will be 0, 0, 1 times um, uh, 1/square root of 2 times 1, 1, 0. So again, that's 0. So psi1 is perpendicular to psi3, and psi look at psi2, the inner product of psi2 and psi3. So that's psi3 times psi2. And we have 0, 0, 1 times 1/square root of 2 times 1, negative 1, 0. So again, that's 0. So this means psi2 is perpendicular to psi3. So this shows that psi2, sorry, this shows that this set of vectors, psi1, psi2, and psi3, they are it is a non-zero orthogonal set. And now let's check if it's orthonormal. So for it to be orthonormal, every vector in this set will have to have its norm equal to 1. So here we check the norm of psi1. It's going to be the square root of the inner product of psi1 and itself. And that's going to be the square root of this summation here. So maybe I should just write it out. So the square, so we know that the inner product of psi1 and psi1 will be the complex conjugate transpose of psi1 times psi1, and that's going to be 1/square root of 2, 1, 1, 0 times 1/square root of 2 times 1, 1, 0, and we will have 2/2, and that's 1. So here we have psi1, the norm of psi1 equals to square root of 1, and that's 1. So the next thing we check is the norm of psi2. So here we have the square root of the inner product of psi2 and itself. And again, the inner product of psi2 and itself will be the complex conjugate transpose of psi2 times psi2. And that's going to be 1/square root of 2 times 1, negative 1, 0, and 1/square root of 2 times 1, negative 0. And again, that's 2/2, and which is 1. So we have the norm of psi2 equals to the square root of 1, which is 1. And we can do the same thing again for psi3. So here we have psi3, and the inner product of psi3 and psi3 is just going to be 0, 0, 1 and 0, 0, 1, which is 1. So the norm of psi3 will be the square root of 1, which is 1. So this shows that this set is a orthonormal set of vectors. So this is orthonormal. And we can have the same result for orthonormal basis. So for that, let's look at theorem 4 and corollary 5. So for theorem 4, it basically says if the set of vectors is an orthonormal basis for an inner product space H, then any vector f in H will emit a decomposition of the form f equals to f equals to summation of the inner product of f and vk times vk, and k is in this composite. So this is actually just the AK that we have just seen, basically the coordinates of the kth coordinates of f in this orthonormal basis, and let's compare the difference. So just now we have AK equals to f vk over the norms, the square norm of vk. This is for orthogonal basis. And now we have AK equals to just f, the inner product of f and vk. And this is for orthonormal. And you see that the difference is for when the basis is orthonormal, then we don't have to divide the inner product by the square norm of vk, and that's because the square norm of vk in this case is just 1, so we don't have to care about that. And similar results can be obtained for the Parsifal's equality or the Parsifal's formula, and it's written here. And you can derive, and you will see that the only difference here is that we don't have to multiply the square of the absolute value of AK by the squared of the norm of VK. And again, that's because the squared of the norm of VK is equal to 1 in this case. And the same argument can be made for this equality here. So again, that's just basic. So again, the only difference is that now we do not multiply the square norm of vk here, because the square norm of vk is equal to 1. All right, this is the end of today's lecture, and I will see you in the next one.